Most of us first encountered acids and bases through the sour bite of a lemon, slippery soap, and the classic 1 to 14 pH scale. That scale is built on the Arrhenius definition, categorizing substances entirely on their ability to generate hydrogen or hydroxyl ions when dissolved in water. But liquid water is a strict constraint. If you try applying this rule to non-aqueous industrial manufacturing or tracing how heavy metals become toxic inside the human body, the model falls apart. Chemical modeling means choosing the right classification tool for the environment you are analyzing. No single definition covers every scenario. Relying on high school textbook standards for complex environmental or medical problems leads to fatal miscalculations. Real-world stakes require more complex predictive models. Think of the evolution of acid-base chemistry like a camera lens pulling back, progressively widening its field of view to capture a much larger universe of chemical reactions. We can map this evolution across 3 frameworks, nested as expanding layers of predictive power. At the center, we have our tightest focus, the Arrhenius model. It works perfectly, but only if your reactions happen in liquid water. Pull the lens back a step and you reach the Brønsted-Lowry model. Here, we drop the water requirement entirely and define acids and bases by how they exchange protons. Pull back as far as possible, and you hit the Lewis model. Protons drop out of the equation. It maps the transfer of electron pairs, bringing virtually every element on the periodic table into the fold. The trade-off is straightforward. As you move to the outer circles, your predictive scope expands dramatically, but you sacrifice the easy math that makes the inner circles so practical. Let's evaluate that middle circle. The Brønsted-Lowry model focuses on one specific action, tracking hydrogen ions, protons, as they are donated and accepted between molecules. That specific proton tracking mechanism makes it the standard for human physiology. Our bodies maintain homeostasis through a bicarbonate buffer system, which tightly controls the concentration of these protons to keep our arterial blood pH at exactly 7.40. When a patient experiences severe metabolic acidosis, their blood is flooded with excess protons. Clinicians use Brønsted-Lowry math to calculate exact doses of sodium bicarbonate to soak up those protons and stabilize the patient. But this model has a significant blind spot. It ignores the vast number of chemical interactions that do not involve hydrogen at all. Brønsted-Lowry is highly effective for fast biological math. Yet, if you need to solve an inorganic or industrial problem, it lacks the variables you need. To capture those non-hydrogen reactions, the Lewis model forces a shift in perspective. By abandoning protons entirely, it tracks electron pair acceptors and donors. Focusing on electrons expands the list of acids to include metal ions like silver and iron, making it possible to analyze reactions in completely non-aqueous environments. The cost of this expansion is steep. We abandon simple concentration math and adopt abstract quantum mechanics, specifically predicting interactions between frontier orbitals. Because we are now mapping the geometry and energy of shifting electron clouds, calculating exact equilibrium constants becomes significantly more complex than basic pH math. The Lewis model accounts for the full scope of chemical reactions, but it forces scientists to grapple with invisible forces rather than easily measurable liquids. To actually use the Lewis model without getting bogged down in complex orbital math, chemists rely on the hard-soft acid-base, or HSAB, theory. This visual matrix categorizes interacting molecules based on 3 main variables: their size, their electrical charge, and their polarizability. Hard substances are compact. They have high charges and tightly held electrons, making them non-polarizable. Soft substances are the opposite. They are larger, with massive, easily distorted electron clouds that are highly polarizable. This classification leads to a highly effective predictive rule. Hard acids prefer to bind with hard bases, and soft acids prefer to bind with soft bases. Grasping polarizability requires a steep learning curve. But applying this pairing logic is the most reliable way to predict stability in complex inorganic chemical systems. To see where the Lewis and HSAB frameworks become a matter of life and death, we have to look at environmental science. Healthy soil relies on its cation exchange capacity, a system of negative charges holding on to vital nutrients like calcium and magnesium. Acid rain disrupts this balance, stripping those nutrients away from plant roots. HSAB theory maps exactly how this acidification causes heavy metal pollutants, like mercury and lead, to detach from soil particles, suddenly becoming mobile and highly toxic in our waterways. That same framework is heavily utilized in massive industrial processing, creating chemical catalysts, smelting raw metals, and fabricating modern semiconductors, all require precise control over highly polarizable, soft acid and base reactions. And when soft heavy metals escape those industries and enter our bodies, HSAB predicts the exact damage. They bind aggressively to the soft sulfur groups in our proteins, shutting down cellular function. Without the predictive power of the Lewis and HSAB frameworks, understanding modern industrial pollution and preventing ecosystem collapse would be nearly impossible. Choosing the right chemical model comes down to a clear decision matrix based on your specific scenario. If you operate in a clinical environment, monitoring patient respiration or performing routine lab titrations, your path is direct. Stick to the Brønsted-Lowry model. Its simplicity and speed make it the optimal tool for calculating water-based proton transfers. If your work involves advanced inorganic chemistry, tracking heavy metal pollution, analyzing soil toxicity, or engineering battery electrolytes, your requirements shift. You need to utilize the Lewis and HSAB frameworks. The right scientific model is the one that allows you to accurately predict your specific outcome.